Welcome to the course Master Number System Conversions in 2.5 hours. If you are studying numbers and you want to master all conversions for whole numbers as well as floating point numbers in an easy way with number animations without spending a huge amount of time and effort. Yes, you are at the right place. Take the course Master Number System Conversions in 2.5 hours. Your instructor is Sara Naseem. She is MPhil in Computer Science and she has done her MS in Computer Science from University of Management and Technology, Pakistan. She has done her BS Honours in Software Engineering from University of Engineering and Technology, Pakistan. She serves as lecturer and also published a research paper. Number system conversions are widely used in areas of computer science, programming, engineering, maths, and electronics. The components of the course are shown on the screen. Using PowerPoint animations, the course offers a great way to learn conversions using minimum time and effort. To make understanding better, the course offers 3 assignment, quiz, and a lot of examples. By the completion of the course, you can apply number system conversions in different areas of computer science, as these 4 number systems are widely used in computer architecture, programming, electrical engineering, maths, and electronics. So if you want to learn number conversions, what are you waiting for? Please enroll now. We would love to have you as part of the course. Thank you. So, today we are going to study about the conversions of different computer number system, which is essential to know before taking a programming course. We humans communicate with each other using letters, numbers, and words, but computer only understand numbers. So whenever we enter any digit or character in the computer, it is converted into a number. For example, if we enter the letter A, it will be converted into a number. Or we enter any digit, it will be converted into a number as well. Or we enter any sign like @ sign or $sign, it is converted into number as well. Why into number? Because computer only understands numbers. And these numbers are represented in a computer using 4 number systems. So it is extremely essential to know about those number systems and their conversions before learning a programming language or taking any other computer course, because number systems are part of computer basics. Before starting the course, my assumptions are that you are already familiar with the topics: what is binary, units of data, and the types of computer number system, because course title shows that it handles the conversions between the computer number systems. So consequently, the course gives a short intro to these topics, not detailed, just to revise the background in order to assist the student. What you will learn here are computer number system conversions in detail. So our main focus is only on the conversions between the different types of number systems, and it handles whole numbers as well as floating point numbers too. So the course gives a brief summary to the following topics: what is binary, units of data, and the types of computer number system, and then explains number system conversions in detail. So let's first revise the basics to understand the course fully. Now, if we ever look at a switch button, it only has 2 options, 1 and 0. 1 means on and 0 means off. As we know that computers use electricity to work, so each computer has a number of circuits inside on chip known as microchip, which you can see on the screen, which is green in color. Like all other circuits, circuits on the microchip are either on or off, which is represented by the symbols 1 and 0. This is called as binary, and the number system that deals with binary is called as the binary number system. So binary number system deals with numbers that are only in the form of zeros and ones, as you can see on the computer screen. As we know, computers work on data, so the smallest unit of data in a computer is called 1 bit. So the value of 1 bit is either 0 or the value of 1 bit is either 1. And when 8 bits are together, they form a next larger unit of data, that is 1 byte. Let's look at some of the units of data from smallest to larger ones. So before going into the detail of the number system, it is essential to understand the units of data in computers. As we said so, smallest unit is bit, which is either 0 or 1. And next unit is byte. So 1 byte is equal to 8 bits. As we can see in the figure, this one box is 1 bit that can contain either 0 or it can contain 1. So these 8 boxes together in memory make what? These 8 boxes together in memory make 1 byte. Next larger units of data are 1 kilobyte is equal to 1024 bytes, or we can say 1024 bytes are equal to 1 kilobyte, or we can say 1 KB. But wait a minute, why is it 1024 and why not 1000? Because 1000 is 1000 and here we are talking about 1024. That's because computer works only in numbers that are powers of 2. 2 raised to power 10 makes 1024, not 1000. That makes 1000. So we will use 1024 rather than writing 1000 because it is a power of 2. So once again I repeat that 1024 bytes equal to 1 kilobyte. The next larger unit of data is 1024 kilobytes equal to 1 megabyte, or you can say 1 MB. And 1024 megabyte make 1 gigabyte. And 1024 gigabyte make 1 terabyte. So we read about the units of data. First of all, we read about 1 bit. Then 1 byte is equal to 8 bits. And then 8 bits make up 1 byte. And then 1024 bytes make 1 kilobyte. And 1024 kilobytes make 1 megabyte. And 1024 megabyte make 1 gigabyte. And 1024 gigabytes make 1 terabyte. So now we are familiar with the units of data. So let's move ahead towards type of number systems used in computer to represent data. So now we are familiar with the units of data. So let's move ahead towards type of number systems used in computer to represent data. But the question is, does the computer deals with only binary system? The answer is no. There are various number systems like we heard of whole numbers and real number in mathematics. But computer mainly deals with 4 number systems and it represents data in these 4 number systems. So let's find out which are they. First of all, we have the number system that is binary number system that we already explained before. A binary number system has a base 2. Why base 2? Because a binary number system deals only with 2 numbers which are 0 and 1. Every number is represented with zeros and ones only. As you can see in the figure, a binary number is shown here, that is 11010. And have you noticed what is this little 2 showing? it's showing that the number has the base 2 and it is a binary number. So bases are written like that with the number. The next type of computer number system is decimal number system. So decimal number system has the base 10, means it has only 10 digits from 0 till 9, and the numbers are represented using these 10 symbols that are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Decimal number system is the one that humans use in our daily life, or you can say that decimal number system is the number system that we read in mathematics. So as you can see in the figure, a decimal number is shown, for example 219. And can you see the base here? Yes, it is 10. Why 10? Because it deals with 10 digits only. Okay, the next type of computer number system is octal number system. So octal has the base 8, means it has only 8 digits from 0 till 7, and the numbers are represented using these 8 symbols that are 0, 1, 2, 3, 4, 5, 6 and 7. So as you can see in the figure, an octal number is shown, that is 1736. And can you see the base here? Yes, it is 8 here. Why 8? Because it deals with only 8 digits, or you can say 8 symbols. The next type of computer number system is hexadecimal number system. So hexadecimal number system has the base 16, means it has total 16 digits from 0 till 15, and the numbers are represented using these 16 symbols that are 0, 1, 2, 3 and so on till 15. But there is one important point to note, that the numbers from 10 to 15 are represented using capital ABC. So 10 is represented as A, 11 as B, 12 as C, 13 as D, 14 as E and 15 as F. So as you can see in the figure, a hexadecimal number is shown, that is C23E. And can you see the base here? Yes, it is 16 here. Why 16? Because it deals with 16 digits, or you can say 16 symbols. Plus you can also see that this capital C shows 12 and this capital E shows 14 in the hexadecimal number shown here. So now we summarize the computer number system by using a table to keep the major concepts in our mind. So first of all, we have the binary number system that has the base 2 and the digits used are 0 and 1 only, and this is an example that only has 2 digits in it, either 0 or 1. The next number system is octal that has the base 8 and it has digits from 0, 1, 2 till 7, means it only has 8 digits. And you can see the example here, 175. So we can see that each digit lies between 0 till 7. We cannot use digits greater than 7 here, as the number does not remain octal anymore. So the next number system is decimal, which has the base 10, and the digits used in this number system are 0, 1, 2 till 9. As you can see this number 569, which is the example here, each digit lies between 0 till 9, and we cannot use digits that are greater than 9, as the number does not remain decimal anymore. So last number system is hexadecimal number system. Hexadecimal number system has the base 16s. That means that the symbols used in this number system are 16, from 0, 1, 2, 3, 4 till 15. So this is the example of the hexadecimal number system. And as you can see this number F0, F0 is represented using digits and each digit lies between 0 till 15. So what is F here? F is 15, just like we stated before. We cannot use digits that are greater than 15 here, as the number does not remain hexadecimal anymore. So now we have given a brief introduction to the 4 number systems that are used in computer, as this course basically explains the conversion. So we move ahead to conversion roadmap, where we will see how can we convert one number system to another. So this is the conversion roadmap, and we will do the conversions for whole numbers as well as floating point numbers. So let's see which conversions we are going to cover. So first of all, we will see how to convert octal number system into binary and then binary into octal. Next, we will see how to convert hexadecimal number system into binary and then binary into hexadecimal number system. Remember, for the octal into binary and binary into octal and hexadecimal into binary and binary into hexadecimal, we will use table for these 4 conversions. So you have to remember this point carefully. Next, we will convert the octal number system into hexadecimal, and this conversion is not direct. So first of all, we convert octal into binary and then binary into hexadecimal. Next, we will see how to convert hexadecimal into octal, and this conversion is again not direct. So we will convert hexadecimal number system into binary first and then binary into octal. Next, we will see how to convert a decimal number system into other bases. So we will see how to convert decimal into binary and then decimal into octal and then decimal into hexadecimal. Next, we will see how to convert other bases into decimal. So we will find out how to convert binary into decimal and then octal into decimal and then hexadecimal into decimal. So these are all of the conversions that we are going to cover, and it does not miss any conversion from one base to another. So first of all, we will see how to convert octal number system into binary number system and then binary number system into octal number system. And remember that whenever we will convert octal into binary or binary into octal, we will use table for that. So before starting conversions, we have to do one thing, that is making a table. Always remember that when we are going to convert a number from octal to binary or from binary to octal, we will make the table. Once the table is made, then it becomes easy to make conversions. So we need some information to make the table. We know that the binary has the base 2 and the octal has the base 8. So what should be the power of 2 to get the answer 8? So now we find out. So we can see 2 multiplied by 2 is equal to 4 and 4 multiplied by 2 is equal to 8. So 2 raised to power 3 is equal to 8. Or we can say that 2 is multiplied 3 times to make 8. So the power of 2 to get the answer 8 is 3. Now let's see how to make the table. As we saw in the previous slide, that 2 raised to power 3 is equal to 8. So we will create a table that has 8 rows and 3 columns. Because 2 raised to power 3, so columns will be 3. And 2 raised to power 3 is equal to 8, so the table will have 8 rows. the table will only contain zeros and ones. Each column has value that refer to powers of 2 starting from right till left. So the rightmost is 2 raised to power 0, as we know that 2 raised to power 0 is 1. The next is 2 raised to power 1, and we know 2 raised to power 1 is equal to 2. And the next is 2 raised to power 2, and we know that 2 raised to power 2 is equal to 4. So if the value in the box is 1, that means that the value is 1. If the value in the box is 0, that means that the value is 0. So here in this box, if the value is 1, that means that the value will be 4, not 1, because 4 is at the top of it, so 4 will be the value. So now we will see how to fill the table with zeros and ones. So first of all, as the table is made for octal numbers, so we take 8 and divide it by 2. Because we are dealing with binary, so we will divide it by 2. So 8 divided by 2 is equal to 4. So now we have 4 here. So in order to fill the table, we will write 4 times 0. So 4 zeros come in the leftmost column. And then we will write 4 times 1. So 4 ones come here in the remaining boxes of the leftmost column. So now we take this 4 comes here, and then we divide it by 2. So 4 divided by 2 is equal to 2. So we have 2 here. So we write 2 times 0 in the next column. 2 times 0, and then we will write 2 times 1. So 2 ones come here. Still some boxes of this column are empty. So again repeat. Write 2 times 0, so 2 zeros come here, and then write 2 times 1, so 2 ones come here. Now the column is completely filled, so we will move to the next column. So now we will take this 2 here, and then again we divide it by 2, which is equal to 1. So we have 1 here, so we write 1 times 0 in the last column. So 1 0 come here, and next we write 1 times 1. So 1 comes here. Is the column completely filled? No, the column is not completely filled. So we will carry on till the whole column is filled. So again write 1 times 0 because we have 1 over here, and then write 1 times 1. Then again 1 times 0, then again 1 times 1. Again 1 times 0, and then again 1 times 1. So now the table is completely filled. And the values of these rows can be calculated by looking at these numbers. So this row, the whole row is equal to 0, this whole row is equal to 1, and this whole row is equal to 2, and so on. But the question is, how did we calculate the values? As this table only contains zeros and ones, so how can we calculate the values greater than 1, that is 2, 3, 4, 5, 6 and 7? So as we know that the value of this column is 1 because 2 raised to power 0 is 1, as I have previously told you, and 2 raised to power 1 is equal to 2. So value of this column is 2, and 2 raised to power 2 is equal to 4. So the value of this column is 4. If the box under 4 is 1, so the value of this box is equal to 4. And if the box under 4 has value 0, then it means that the value of this box is 0. Similarly, if the value under box 2 is 1, the value is 2. And if 0, then the value of this box is 0. And if the value under the box 1 is 1, that means that the value of this box is 1. And if the value under the box is 0, then the value is equal to 0. So let's further understand by looking at an example. So if we want to see how did we calculate the value of 5? So we come here. So the value under the column 1 is equal to 1. That means that its value is equal to 1. Next we come to the middle column. So if the value under 2 is equal to 0, so that means that the value is 0. And then we come here, and if the value under 4 is 1, that means that the value is 4. So finally we add them all together. 4 plus 0 plus 1 is equal to 5. So this is how these values are calculated. So listen carefully and remember that we will make this table when we are converting from binary into octal or from octal into binary. So now remember it. So now we have created the table. So we will start conversions. So first of all, we will learn how to convert octal number system into binary. So we will use table for that. So let's move ahead. So now we will see how to convert an octal number into a binary number. And we are dealing with the whole number here. Okay. So we are given with the whole number 25 in octal and we have to convert it into binary. So we know that 2 raised to power 3 is equal to 8. So we add table that we created before that shows octal numbers from 0 till 7 in their binary equivalents. So now we see that we are given with the value 25. So first of all, we look at the value 2 and we will find it in the table. So where is the value 2 in the table? So as we can see, 2 is here and it is equal to 0, 1, 0 in binary. So we write 2 as 0, 1, 0. Next we will take the digit 5 and we will look at the table. So where is 5 in the table? Here is 5 in the table and 5 is equal to 1, 0, 1 in binary. So we write 5 as 1, 0, 1. So now we have calculated the value of 2 and also calculated the value of 5. So we will combine the result of these two to get the final answer. So this is the final answer 0, 1, 0, 1, 0, 1. As we know that the 0 towards the left side of the number is always optional. So we will omit it in writing the final answer. So this is the final answer and we can say that the number 25 in octal is equal to 10101 in binary. So now we are done with octal into binary conversion for whole numbers. In the next example, we will look at the floating point number. Now we will convert an octal number into binary number using a floating point number. So the floating point number we are given is 76.4 in octal and we have to convert it into binary. So we know that 2 raised to power 3 is equal to 8. So we add table that we created before that shows octal numbers from 0 till 7 in their binary equivalents. So first of all, we will look at the number 7 and we will find it in the table. So where is the number 7 in the table? Here is the number 7 in the table and it is equal to 111. So we write 7 as 111. Next we will look at the number 6. So where is the number 6 in the table? Here is the number 6 and it is equal to 110 in binary. So we write 6 as 110. Next, the decimal point will remain at its position and next we will find the number 4 in the table. So where is the number 4 in the table? Here is the number 4 and it is equal to 100 in binary. So we write 4 as 100. So in the end, we will combine the result together and the decimal point will remain at its place. So the final answer is 111 and then 110 and then comes the decimal point and then 100, which is the final answer. So now we can say that the number 76.4 in octal is equal to 111.110.100 in binary. So this is how we learn how to convert an octal number into a binary number for floating point numbers. So in the next section, we will see how to convert binary into octal, and again we will use table for that. So let's move ahead. So now we look at an example in which we are going to convert a binary number into an octal number. And remember, in this example, we are going to use the whole number. So we are given with the number 10110 in binary, and we have to convert it into which base? That is octal. So remember, as we did previously, that 2 raised to power 3 is equal to 8. So now we add the table that we created before that shows octal numbers from 0 till 7 in their binary equivalents. These are the binary equivalents, okay? So now we are given with the binary number 10110. So now we will make group of 3 digits while moving away from the decimal point. Why 3? Because 3 bits are used to represent octal numbers, as you can see in the table. For example, 7 is represented using 3 bits that are 1, 1 and 1. And number 2 is represented using 3 bits that are 0, 1 and 0. So, in order to make groups of 3 bits, we will move away from the decimal point and keep on making groups till the last digit. So now you must be wondering, where is the decimal point in this whole number? So when we are talking about mathematics, whole numbers do have a decimal point at the end, which is normally invisible. So we know that the decimal point is at the end of this digit. So we will move away from the decimal point and consequently moving from right till left, and we will make groups of 3 bits. So now we see in this group we have 3 digits that are 110, and in this group we have 2 digits but we want 3 digits. So we will add a 0 to make them 3. So now we have made groups of 3 bits. So first of all, we look at the group 010 and we find it in the table. So where is 010 in the table? Here is 010 in the table, and we can see that it is equal to which octal digit? That is 2. So we will write 2 here. Next we have the number 110. So we will find the number 110 in the table. So where is 110? Here is 110 in the table, and it is equal to which digit? That is 6. So we write 6 here. So now we combine the answer, and that makes 26 in octal. So now we can say that the whole number in binary, that is 10110, is equal to 26 in octal. So this is how we can convert a binary number into an octal number. So now we see how to convert a binary number into an octal number. And remember, in this example, we are dealing with the floating point number. Previously, we were dealing with whole numbers, and in this example, we are dealing with the floating point number. So, we are given with the number 11.10 in binary, and we have to convert it into octal. So, we know that 2 raised to power 3 is equal to 8. So, we will use a table that has 8 rows and 3 columns, and it is filled with zeros and ones, and we previously did how to fill the table. So this is the number 11.10. So what we will do next? So now we will make group of 3 bits while moving away from the decimal point. So for this number, we will move from right till left as the decimal point is here. And for this number, we will move from left till right as the decimal point is here. So we will move away always for whole numbers as well as for floating point numbers. So now we have created the groups. So we can see that the group has 2 digits and we have to make group of 3 bits. So we will add 10 to it, and also we will add 10 to it. So now the group of 3 bits are completed. Once completed, we will look at their values in the table. So first of all, we will find the value 011. So where is the value 011 in the table? Here it is. We can see that 011 in binary is equal to which digit? That is 3. So we will write 3 here. Now we add the decimal point. So the decimal point comes to its place. Next, we have the digit 100. So we will find the digit 100 in the table. As we can see that the bits 100 are here in this row, and they are equal to which octal number? That is 4. So we will write 4 here. So finally, we can say that the number 11.10 in binary is equal to 3.4 in octal. So 3.4 is the final answer, and that is the octal number that we needed to calculate. So we have done octal into binary conversion and binary into octal conversion by using a table. In the next section, we will do hexadecimal into binary and binary into hexadecimal, again by using the table. In the next section, we will do hexadecimal into binary and binary into hexadecimal, again by using the table. Now let's see how to make the table. In the previous slide, we saw that we are dealing with hexadecimal and binary conversions. So 2 raised to power 4 is equal to 16. So we will create a table that has 16 rows, and the table has how many columns? 4. Why 4 columns? Because 2 raised to power 4 is equal to 16. Once again, the table will only contain zeros and ones. So we can see that the value of each column is represented by powers of 2 starting from right till left. So 2 raised to power 0 is 1, 2 raised to power 1 is equal to 2, 2 raised to power 2 is equal to 4, and 2 raised to power 3 is equal to 8. So the value of this column is 1, and this column is 2, and the value of this column is 4, and the value of this column is 8. And the hexadecimal numbers from 0 till 15 are written here. By using the table, we will fill out the binary values that are equal to those hexadecimal numbers written here. Once done, it will help us in performing the conversions. So now we see how to fill the table with zeros and ones. So first of all, we know that the base of hexadecimal is 16. So we divide 16 by 2. Why 2? Because we are dealing with hexadecimal and binary conversion, and binary has the base 2. So we divide 16 by 2 and we get 8. So how will we fill the table? We can see once we get 8, we write 8 times 0. So 8 zeros come in this column. And then write 8 times 1. So 8 ones come to this column. Now this column is filled. Now we will go to the next column. So now we take this number 8 and again we divide it by 2, and 8 divided by 2 is equal to 4. So now we have 4 here. So we will write 4 times 0. So 4 zeros come here, and then we will write 4 times 1. So 4 ones come here. Still some boxes of this column are empty. So again repeat the same procedure. Write 4 times 0. 4 zeros come here, and again write 4 times 1. So 4 ones come here. Now the column is full, so we will move to the next column. So now we will take this 4 and we will divide it by 2. So 4 divided by 2 is equal to 2. So we write 2 times 0. So 2 zeros come here, and then we write 2 times 1. So 2 ones come here. Is column completely filled? No, the column is not completely filled. So write 2 times 0 again. 2 zeros come here, and again write 2 times 1. So 2 ones come here. So carry on till the whole column is filled. 2 times 0, 2 times 1, 2 times 0, 2 times 1. So next we will take the number 2 and we will divide it by 2. So 2 divided by 2 is equal to 1. So now we have 1 here. So in order to fill this column, we will write 1 times 0. So 1 0 come here, and again write 1 times 1. So 1 1 comes here. Is the column completely filled? No, the column is not completely filled. So again write 1 times 0. So 1 0 comes here, and again write 1 times 1. So 1 1 comes here. So we will carry on this procedure till the whole column is filled. So 0. So 1 times 0, 1 times 1. 1 times 0, 1 times 1. 1 times 0, 1, 0, 1, 0, 1, 0, 1. So now we have filled the table. So now let's see how the values are calculated using this table. So if we want to see how the values are calculated, for example, we want to calculate the value of 1010, and we want to see how this value in binary is equal to 10 in hexadecimal, or you can say A in hexadecimal. Alright. So first of all, we will look at the column 1 and we will see that the value under column 1 is 0. So the value of this box is 0. Next we will see the column 2 and we will see that the value under the column 2 is 1. So the value of this column is 2. Next we will come to this box and we will see that the value under the column 4 is equal to 0. So its value is 0. And next we will come to this box and we will see value under the column 8 is equal to 1. So the value is 8 here. So now we will add them all together. We have 8 here plus 0. 8 plus 0 is equal to 8. 8 plus 2 is equal to 10. And then 10 plus 0 is equal to 0. So the final value calculated from these 4 boxes is equal to 10. So this is how we can say that this value is equal to A in hexadecimal, or you can say 10 in hexadecimal. So this is how these all values are calculated and written here. So we can say that 0 is equal to this, 1 is equal to this, 2 is equal to this, and so on till F. So now we have created the table. So now we will see how to convert hexadecimal into binary first by using the table. So now we have created the table. So now we will see how to convert hexadecimal into binary using this table. So let's look at the examples. So first of all, we will see how to convert a hexadecimal number into binary, and in this example, we are dealing with the whole number. So the number that we are dealing, or you can say that the example that we are dealing in this question is 64. And we have to convert it into binary. So we know that 2 raised to power 4 is equal to 16. So we will have the table that has 16 rows and 2 raised to power 4 is equal to 16. So we will have a table that has 4 columns. So first of all, we will look at the value 6 and we will find the value 6 in the table. So where is the value 6 in the table? Here is the value 6 in the table. So the binary value of 6 in the table is 0110. Remember, we calculated the binary value of these digits while we were dealing with octal and binary numbers. So we will calculate the values in the same way. So the binary value of 6 is 0110. So we write 6 as 0110. Next we have the digit 4. So we will find the value of the digit 4 in the table. So where is the digit 4 in the table? Here is the digit 4 in the table. And the binary value of 4 is 0100. So we can write 4 as 0100. So now we have calculated the value of 6 and as well as the value of 4. And no more digits are in the example. So we will combine the binary value of 6 and the binary value of 4. So now we can say that the answer is 0110 from here and 0100 from here. So now we can say that 64 in hexadecimal is equal to 01100100 in binary. So this is how we can calculate hexadecimal into binary using whole numbers. In the next example, we will see how to convert hexadecimal into binary using the floating point number. So here the number given is 5c.e in hexadecimal and we have to convert it into binary. So we know that 2 raised to power 4 is equal to 16. So we have the table that has 16 rows and 4 columns. Alright. So first of all, we have the number 5. So we will find the number 5 in the table. So where is the number 5 in the table? Here is the number 5. And the binary value of 5 in the table is 0101. So we will write 5 as 0101. Next we will look at the value of c. So we will find the value of c in the table. Where is the value of c in the table? Here is the value of c in the table. So the binary value of c in the table is 1100. That is actually 12. So we will write c as 1100. Next comes the decimal point. So the decimal point will maintain its position. So it comes here. And the next digit we have is e. So now we will find e in the table. So where is the letter e in the table? Here is the letter e. And we know that e is 14. And the binary value of e is 1110. So we write e as 1110. So now we have calculated all the 3 values of the 3 digits that are given. If we have more digits in the example, then we will calculate the binary value of all of the digits. So now we have calculated the binary value of these 3 digits 5, c and e. So we will combine them all together to become one number. So now we can say that 0101 comes from here, 1100 comes from here, and next we have the decimal point that will maintain its position, and 1110 comes from here. So now we can say that the number 5c.e in hexadecimal is equal to 01011100.1110 in binary. So this is how we can calculate conversion of hexadecimal number into binary using the floating point number. So now we will see how to convert a binary number into hexadecimal number, and in this example we are dealing with the whole number. So in this example we are given with the whole number 1001101 in binary, and we have to convert it into hexadecimal. So we know that 2 raised to power 4 is equal to 16. So we will have the table that has 16 rows and 4 columns. So what we will do here is that, so just like the conversion of binary into octal, we made group of 3 bits. Alright, in the same way, in this example, we will make group of 4 bits. Why 4 bits? Because hexadecimal number is represented using 4 bits. Just like you can see here that the number from 8 till 15, they can be represented using 4 boxes, and one box is 1 bit. So 4 bits are used to represent a hexadecimal number. And octal number is represented using 3 bits. Just like we did the conversion of binary into octal. So there we made the table that has only 3 columns. So in this case we will have a table that has 4 columns because we are dealing with 4 bits. Alright. As we need 4 bits to represent a hexadecimal number, so we will make groups of 4 bits. And we will make the group while moving away from the decimal point. So remember I told you before that for whole numbers, there is a point towards the right side of the whole number that is invisible, and in mathematics we consider that there is a decimal point. But we do not need to mention it. So if we analyze the rule that we have to move away from the decimal point and an invisible decimal point is here at this point, so we will move away and we will make a group of 4 bits. So now we make a group that has 1101 and the remaining digits left are 100. So we will make the group while moving away from the decimal point. So while moving from right till the left. So now we can see that this group of 4 bits is complete. But if we look at this group, then it has 3 bits and we need 4. So what we will do, we will add a 0 to make them 4. Just like this. So now the groups of 4 bits are completed and no more digits are there in the example. So we will calculate their equivalent hexadecimal value by looking at the table. So first of all, we will find the binary value 0100 in the table. So where is the binary value 0100 in the table? Here is the binary value and it is equal to which digit in hexadecimal? That is 4. So we write 4 here. Next we have the group 1101 and we will find it in the table. So where is 1101 in the table? Here is 1101 in the table and it is equal to which value in hexadecimal? That is D. So we write 1101 as D. So now we have calculated all the values, so we can write the answer as 4D in hexadecimal. Or you can say that the number 1001101 in binary is equal to 4D in hexadecimal number system. So this is how the conversions are done of binary number into hexadecimal number. So in the next example, we will see how to convert a binary number into hexadecimal number using a floating point number. So we know that 2 raised to power 4 is equal to 16. So we will have the table that has 16 rows and 4 columns. So now we write the value here 11.1101. So remember, we will make groups of 4 bits while moving away from the decimal point. So in this case, we will move from right till left and we are moving away from the decimal point. And in this case, while moving away from the decimal point, we are moving from left till right. So this is how we can make group of 4 bits. So this group is complete because it has 4 bits. But if you look at this group, it is incomplete. It has 2 bits and we need 2 more bits. So we add 2 more zeros to it to make them complete. So now both the groups are complete, so we will find their values in the table. So first of all, we will find the value 0011 in the table. So where is the value 0011 in the table? Here is the value 0011 and it is equal to which hexadecimal digit? That is 3. So we write 3 here. Next comes the decimal point and it will maintain its position. Okay, now we have the second group 1101 and we will find the binary value 1101 in the table. So where is the binary value 1101 in the table? So now we can see that the value is here 1101 and it is equal to D. So we write D here. So now we have calculated the value and no more digits are left. So we will say that the answer is 3.D, or you can say that the binary value 11.1101 is equal to 3.D in hexadecimal. So this is how we can convert a floating point number that is given in binary into hexadecimal base. So now we have completed octal into binary, binary into octal, hexadecimal into binary and binary into hexadecimal. In the next section, we will see how to convert octal into hexadecimal. So now we are going to look at the solutions of assignment number 1. And first of all, we go to question number 1 and look at its solution. So let's move ahead. So here we have the question. In this question, we have to convert an octal into a binary. So this is question number 1 in which we have to convert 3456 in octal and we have to convert it into binary. So here is the number written 3456. Next what we are going to do is that we are going to pick the first digit, which is 3, and we will find its value inside the table that we created in the starting videos. If you don't know how to create the table, you can look at those videos and understand it. Alright, so here is 3 in the table, and what is the binary value of 3 in the table? That is 011. So we write 3 as 011. Next we have the value 4 and we will find the value of 4 in the table. So here is the value of 4 in the table and 4 is equal to 100 in binary. So we write 4 as 100. Next we will look at the value of 5 and we will find 5 in the table. So here is 5 in the table and 5 is equal to 101 in binary. So we write 5 as 101. Next we look at the value of 6 and if we go to the table we can find 6 here and 6 is equal to 110 in binary. So we write 6 as 110. So we combine these 4 values and calculate this answer. So now we can say that the number 3456 in octal is equal to 0111 0010 1110 in binary. So this is how we can solve question number 1. Next we move to question number 2 and its solution. So in question number 2 we have to convert an octal into binary using floating point number. Alright, so this is the question and we have to convert 26.47 in octal into binary. Alright, so here is the number 26.47 and again we will look at the table and we will find the binary values of these digits in the table. So first of all we have the number 2 and we will go to the table. Here is 2. So 2 is equal to 010 in binary. So we write 2 as 010. Next, we will look at the digit 6 and we will go to the table. Here is 6. So 6 is equal to 110 in binary. So we write 6 as 110. Next, the floating point will come here and then we have the number 4. So we will find the number 4 in the table. So here we can find number 4 in the table. So 4 is equal to 100. So we write 4 as 100. And next we move to 7 and here is 7 in the table and 7 is equal to 111 in binary. So we write 7 as 111 here. So next we will combine these all digits together to calculate our answer. So we combine all them and they become 010 comes from here, 110 comes from here, then we have the floating point number, then 100 comes from here and 111 comes from here, right? So now we can say that the number 26.47 in octal is equal to 10110.1001111 in binary. So this is how we can calculate the solution of question number 2. Next we move to the solution of question number 3. And in this solution we have to convert a binary number into an octal number, right? So we are given with this question that we have to convert 1111.101 in binary and we have to convert it into octal. Alright. So first of all, what we do here is that we will make, as we have to convert a binary number into octal, so we will make group of 3 digits while moving away from the decimal point. So while moving towards left, we will make group of 3. So that is 111. 111. Okay, they come here. Next, only one is left. So we write 1 here. So we know that we have to make group of 3 bits in order to convert it into octal. And here we have only 1 digit. So we will add 2 zeros to that to make it 3 digit, right? So we have completed this group and next we move towards the right side of the decimal point. And here we can see that we have 3 digits, 101. So we can make their group and the group is complete. Now we will look at the table and we will write the equivalent octal numbers by looking at the table. So first of all, we have 001. So we will go to the table and find 001. So here is 001 and 001 is equal to 1. So we write 1 here. Next we have 111. So we can find 111 in the table here. And it is equal to 7. So we write 7 here. Then the decimal point comes here. And next we have 101. 101 is here in the table, right? And it is equal to which digit? That is 5. So we write 5 here. So now we can say that the number 1111.101 in binary is equal to 17.5 in octal. So this is how we can solve this question. Next we move to question number 4 solution. So in this question we have to convert a hexadecimal number into binary and we are going to use the whole number for that. So we are given with the number FD9 in hexadecimal and we have to convert it into binary. So we write the number FD9 here. So what we will do here is that again we will tally the table. If you don't know how to make the table, you can look at the previous videos, right? So first of all, we have the letter F. So we will find the letter F in the table. So we can see that F is here. And F is equal to 1111 in binary. So we write here 1111. Next we have D. So we will find D in the table. So here we can find D in the table. So D is equal to 1101 in binary. So we write D as 1101. Next digit we have is 9. So we will find 9 in the table. So here is the digit 9. And 9 is equal to 1001 in binary. So we write 9 as 1001. Next we will combine this value and this value to get the final binary values, which we can see here. So we can say that the number FD9 in hexadecimal is equal to 111111011001 in binary. So this is how we can solve this question. Next we move to the solution of question number 5, and we can see that in question number 5 we are given with the binary number and we have to convert it into hexadecimal. So this is the number we are provided in binary and we have to convert it into hexadecimal. So what we will do here is that again we will make group of 4 bits while moving away from the decimal point. So when we move towards the left side, we see that we have 3 digits 0, 1, 1. So we write here 0, 1, 1, but we have to make group of 4 digits and we have 3, so we add 1, 0 to it to make them 4 bits. Next we are going to move towards the right side from the decimal point. So here we make the group of 4 bits 1, 1, 0, 1. Alright, so this group is completed, and next we are left with only 2 digits, that is 1, 1, and we write 1, 1 here. But we know that we have to make a group of 4 bits, so we add 2 zeros to that. So here all the 3 groups are completed. Once the groups are completed, next we will look into the table and we will find their equivalent hexadecimal value. So first of all, we will find the value 0110 in the table. And where is the value 0110 in the table? Here is the value and it is equal to 6. So we write 6 here. Next we will find the value 1101 in the table. So 1101 is here in the table and it is equal to D in hexadecimal. So we write 1101 as D. Next we have the value 1100 in binary and we will find it. So where is the value? Here is the value 1100 and we have to convert it into hexadecimal. So it is equal to C. So we write 1100 as C. So now we have calculated the value and we will join the complete value to get the final answer. So the final answer is 6.DC, and we can say that this number in binary is equal to 6.DC in hexadecimal. So now we are done with assignment number 1. I hope you understand the solution. I hope that you must have learned from it and you have done the assignment yourself. So now we have completed octal into binary, binary into octal, hexadecimal into binary, and binary into hexadecimal. In the next section, we will see how to convert octal into hexadecimal. The conversion from octal into hexadecimal is not direct. So first of all, we will convert octal into binary and then binary into hexadecimal. And then we will see how to convert hexadecimal into octal. Again, the conversion is not direct. So we will convert hexadecimal into binary first and then binary into octal. So let's see how to do the conversions. So first of all, we see how to convert octal into binary number. So in this example, we have to convert octal number into binary number and we are given with a floating point number. Okay. So we know that 2 raised to power 3 is equal to 8. So we will have the table that has 8 rows and 3 columns. Alright. So first of all, we will look at the digit 6 and we will find the digit 6 in the table. So where is the digit 6 in the table? Here is the digit 6 and its binary value is 110. So we write 6 as 110. Now we move to the next digit, that is 6 again, and we will write 6 as 110. Now comes the decimal point. So decimal point comes here and then we get the digit 4. So now we will find the value of 4 in the table. So where is the value of 4 in the table? Here is the value. So the binary value of 4 is 100. So we write 4 as 100. So now we can say that the final value we calculated is 110. So now we have calculated all the values and we can write the answer as 110 comes from here, 110 comes from here, and then the decimal point maintain its position, and then 100 comes from here. So we can say that the value 66.4 in octal is equal to 110.110.100 in binary. So now we have converted the number from octal into binary and we have completed the first part. Okay. So in the next section we will see we have done this, and now we will see how to convert binary into hexadecimal to complete the conversion octal into hexadecimal. Okay. So now we move ahead. So now we are going to convert binary into hexadecimal just like we did it previously. Alright. And in this example we are dealing with a floating point number. So we are given with an example 111.110.100 in binary, and we have to convert it into hexadecimal. So we know that 2 raised to power 4 is equal to 16. So we have that same hexadecimal table. So now we will make group of 4 bits while moving away from the decimal point, just like we did it previously. So first of all we will write 1110, then we have 11 from here, then comes the decimal point, and then 100 from here. So now while moving away from the decimal point we will make first group, then we will make the second group, and we can see that we need 4 bits to make a group, and in this group we have 2 bits, so we will add 2 more zeros to it, 10 and the second 0. So now when we look at 100, we will move away from the decimal point, that is from left till right. So now in this group we can see that we have 3 bits and we need 4. So we will add 1 additional 0 to it. Alright, so now we have completed the group of 4 bits. So now we will look at their values in the table. So first of all, we will find 1110 in the table. Here is 1110 in the table and it is equal to which digit in hexadecimal? That is E. So we write 1110 as E. Next we will find the value 0011 in the table. So where is the value 0011 in the table? Here is the value 0011 in the table and it is equal to 3. So we write 3 here. Next, the decimal point will maintain its position. So it comes here. And next we will take the binary value 1000 and we will find it in the table. So where is the value 1000 in the table? Here is the value and it is equal to which hexadecimal digit? That is 8. So we write 8 here. So now by combining them all together, we will find its answer. So we can say that the answer is 3E.8 in hexadecimal, or you can say that the number 111110.100 in binary is equal to 3E.8. So remember that this is the final part of the conversion. So we can say that the number 66.4 in octal is equal to 3E.8. Remember we did the conversions into 2 parts. First of all we converted octal into binary and then we converted binary into hexadecimal. So this is the final answer. So now we have done the octal into hexadecimal. In the next section we will see how to convert hexadecimal into octal. And as I told you that the conversion is not direct, so first of all we will convert hexadecimal into binary. Alright, so now we will convert hexadecimal into binary using floating point number. and we have the number 5a.b in hexadecimal and we have to convert it into binary. So we know that 2 raised to power 4 is equal to 16. So we have the table that has 16 rows and 4 columns. First of all, we have the number 5 and we will find it in the table. So what is the binary value of 5 in the table? That is 0101. So we write 5 as 0101. The next number we have is a, and we will find the value of a in the table. So where is the value of a in the table? Here. And the binary value of a in the table is 1010, that is 10. So we write a as 1010. Next comes the decimal point, so it comes here. And the next number we have is b. So we will find the value of b in the table. Where is the value of b in the table? Here is the value of b, and the binary value of b is 1011. So we write b as 1011. By combining them all together, we will find the final result. So we can say that the answer is 01011010.1011 in binary. Or we can say that the hexadecimal number 5a.b is equal to this number in binary. So now we have found the value of hexadecimal into binary, and in the next section we will find the value of this binary number into octal to calculate the final answer, and then the conversion of hexadecimal into octal will be completed. So now we will convert this binary number into octal number. So we know that 2 raised to power 3 is equal to 8. So we will use the table that has 8 rows and 3 columns. So we have this binary number. So we will make group of 3 bits while moving away from the decimal point. So first of all, we have 010. Then we have 011. And then we have 01. No more digits are left. So we will move towards this side. So the next 3 bits we have are 101, and next we have only 1 left. Alright, so now we will make group of 3 bits while moving away from the decimal point. So this group is complete, this group is complete, this group is incomplete. It has 2 bits, we need 3. So add 1 0 to it. Next we come to this group, this is complete, and then this group. This is not complete. It has only 1 bit, so we will add 2 more zeros to it. So now it is complete. So now we will find the respective value into octal using this table. So first of all, we will find the value of 010 in the table. Where is 010 in the table? Here it is. And what is the value of 010 in octal? That is 2. So we write 2 here. Next we will find the value 011 in the table. So where is the value 011 in the table? Here is the value, and it is equal to 3. So we write 3 here. Next we will find this value 001 in the table. So where is this value 001? Here is the value, and it is equal to which octal digit? That is 1. So we write 1 here. Next, the decimal point will maintain its position. So next we have 101. So we will find the value of 101 in the table. Where is the value of 101? Here, and it is equal to which octal digit? That is 5. So we write 5 here. Next we will look at the value of 100 in the table. So where is the value 100 in the table? Here is the value, and it is equal to which octal digit? That is 4. So we write 4 here. So now we have calculated all the values of these groups. So we can write the final answer 132.54 in octal. So now we can write the answer as 01011010.1011 in binary is equal to 132.54 in octal. Or you can say that the number 5a.b in hexadecimal is equal to 132.54 in octal. Remember, we did two steps. First of all, we converted hexadecimal into binary, and then we converted binary into octal. So this is the final result and this is the final answer. So now we have converted octal into hexadecimal and hexadecimal into octal. So now we move to the next section, that is, we will see how to convert decimal into other bases. So now we have converted octal into hexadecimal and hexadecimal into octal. So now we move to the next section, that is, we will see how to convert decimal into other bases. First of all, we will see how to convert decimal into binary. Then we will see how to convert decimal into octal, and then we will see how to convert decimal into hexadecimal. Now remember one thing, that the conversion method used for whole numbers is completely different from the method used for floating point numbers. So first of all, we will see how to convert decimal into other bases using whole number. We will look at the whole number method. So, while converting a decimal into other bases, this procedure is used for whole numbers. We see when we convert decimal into binary, we divide the given number by 2. Why 2? Because the base of binary is 2. That's why. Similarly, when we convert decimal into octal number, then we divide the given number by 8 because base of octal is 8. And in the same way, when we convert decimal into hexadecimal, we divide the given number by 16 because base of hexadecimal is what? That is 16. So, first of all, let's see how to convert decimal into binary. Now, these conversions are for whole numbers first. Once they will be calculated, then we will show you conversions for floating point numbers as well. And remember, the method for floating point numbers is completely different from the method used for whole numbers. So now we see how to convert decimal into binary, and we are given with the whole number. So the whole number is 198 in decimal, and we have to convert it into binary. As we have to convert the number into binary, so we divide the number by 2. So we understand the procedure by looking at the screen, and it's a bit similar to calculating prime factorization. So let's understand it. So we are converting 198 in decimal into binary that has a base 2. So we divide the number 198 by 2. So when we divide the number 198 by 2, quotient is equal to 99 and remainder is equal to 0. So 99 comes here just like it happens in prime factorization, and remainder comes here. Again we have 99, so we will divide 99 by 2. When we divide 99 by 2, quotient is equal to 49 and remainder is equal to 1. So 49 comes here and remainder comes here. Again we divide 49 by 2. So when 49 is divided by 2, quotient is equal to 24 and remainder is equal to 1. So 24 comes here and 1 comes here. So when we divide 24 by 2, quotient is equal to 12 and remainder is equal to 0. So 12 comes here and 0 comes here. So when we divide 12 by 2, quotient is equal to 6 and remainder is equal to 0. So 6 comes here and remainder comes here. So when we divide 6 by 2, quotient is equal to 3 and remainder is equal to 0. So 3 comes here and 0 comes here. Again we divide 3 by 2. So quotient is equal to 1 and remainder is equal to 1. So quotient comes here and remainder comes here. Remember, we will keep on dividing unless we get the number here that is less than 2. So now we can see that the number 1 is less than 2. So we will stop the process. Once calculated, we will calculate the binary number by going from bottom to top like that. So now we can say that the answer is 11000,110 in binary. So this is how the answer is calculated, and now we can say that the number 198 in decimal is equal to 11000110 in binary. And remember, this procedure is followed for whole numbers. So now we have done decimal into binary conversion using whole numbers. In the next slide, we will convert decimal into octal using whole numbers. So here we will convert decimal into octal using whole number. And the whole number that is given to us is 798 in decimal, and we have to convert it into octal. As we have to convert the number into octal, so we will divide the number by 8 using the method prime factorization. So first of all, 798 is divided by 8. So we get the quotient 99 and remainder is equal to 6. So 99 comes here and remainder comes here. Again we divide 99 by 8. So when 99 is divided by 8, quotient is equal to 12 and remainder is equal to 3. So 12 comes here and 3 comes here. In this method again, we will keep on dividing until we get the quotient that is less than 8. So again we divide the number 12 by 8 and we get the quotient is equal to 1 and remainder is equal to 4. So 1 comes here and 4 comes here. Now we can see that this 1 is smaller than 8, so it cannot be further divided. So we will calculate the answer by going from bottom till top like that. So now we can say that the answer is 1436 in octal. So this is how we can convert decimal into octal using whole numbers. So now we have completed decimal into binary and decimal into octal. In the next slide, we will see how to convert decimal into hexadecimal using whole numbers. So here we are given with the number 798 in decimal and we have to convert it into hexadecimal number. So as we have to convert the number into hexadecimal, so we will divide the number by 16. So when the number 798 is divided by 16, so the quotient is 49 and the remainder is E. So 49 comes here and E comes here. So as we know that 49 is greater than equal to 16, so we will divide 49 by 16. So when we divide 49 by 16, we get the quotient as 3 and the remainder is 1. So 3 comes here and 1 comes here. So now we have the quotient 3, which is smaller than 16. So we cannot divide it further and we will stop the procedure. So we will calculate the answer by going from bottom to top like that. So now we can say that the answer is 31E in hexadecimal. So finally we can say that the number 798 in decimal is equal to 31E in hexadecimal. So this is how we convert decimal into hexadecimal using whole numbers. So now we have completed the conversions for decimal into other bases using whole numbers. In the next section, we will see how to convert decimal into other bases using floating point numbers. In the next section, we will see how to convert decimal into other bases using floating point numbers. So first of all, we will see how to convert decimal into binary using a floating point number. And as I have already told you that the procedure is totally different from the procedure of whole numbers. So let's move ahead. So now we will see how to convert decimal into other bases using floating point numbers. So first of all, we will see how to convert decimal into binary. So as we previously mentioned that the procedure of conversion of decimal into binary using whole numbers is totally different from the procedure of floating point numbers. So we will use a different procedure in this example in which we are going to convert our decimal into binary using a floating point number. So we will look at the example, and by looking at the animation, I will make you understand how we are following the procedure, and then you can understand it. So first of all, we are given with the number 0.625 in decimal and we have to convert it into binary. So we will take the number 0.625 and we will multiply it with 2. Why 2? Because we have to convert it into binary, and binary has the base 2. So we will multiply the number with 2. So now we get the answer 1.25. Once we get the answer, then we will write the integer part here and the fractional part here. So integer part is 1, so we write 1 here, and fractional part is 0.25. So we write 0.25 here. And now we will check is the fractional part is equal to 0. And if the fractional part is equal to 0, we will stop the procedure. Alright, so here as we can see that the fractional part is not equal to 0, so we will take this part 0.25 and again multiply it with 2. And we get the answer 0.5. Now here the integer part is 0 and the fractional part is 0.5. Is the fractional part is equal to 0? No, the fractional part is not equal to 0. So again we will take this 0.25 and multiply it with 2. After multiplying 0.5 with 2, we get the answer 1.0. So we write 1 here and we will write 0 in the fractional part. So again we will check is the fractional part is equal to 0? Yes, the fractional part is equal to 0. So now when the fractional part is equal to 0, so we will stop the procedure and we will calculate the answer by going from top to bottom of the integer part. Understand? So in this way we will do it. And we can say that the answer is 0.101. As you can say 0.101. We are going from top to bottom and we are calculating the answer 0.101. The decimal point will maintain its position, that is towards the leftmost side of the number. So decimal point come here and then we have the number 101. So this is how we calculate the answer. So now the number 0.625 in decimal is equal to 0.101 in binary. This is how we can convert decimal into binary using floating point numbers. So now we will see how to convert decimal into octal using floating point numbers. The procedure is almost the same, but the only difference is that when we were converting decimal into binary, we multiplied the number by 2. But in this case, we will multiply the number with 8 because we have to convert decimal into octal and octal has the base 8. So that's why. So here in this example, we are given with the number 0.015625 in decimal and we have to convert it into octal. So let's see how do we solve it. So this is the number given and we multiply it with 8 because base of octal is equal to 8, that's why. So we get the final answer 0.125. So here the integer part is 0 and the fractional part is 0.125. So is the fractional part is equal to 0? No, the fractional part is not equal to 0. So we will take the fractional part and multiply it with 8 again. So we get the answer 1.000, or you can say 1. So now the integer part is 1 and the fractional part is equal to 0. 0.0 or you can say 0. So is the fractional part is equal to 0? Yes, it is 0. So now when the fractional part is equal to 0, we will stop the procedure. And once again in this case, we will calculate the answer by going from top to bottom of the integer part. So now we can say that the answer is 0.01. That is, first comes point and then 0 and 1. See, we are going from top to bottom of the integer part. Alright, so we will calculate it in this way. The decimal point will maintain its place, that is towards the left side of the number. So now we can say that the number 0.015625 in decimal is equal to 0.01 in binary. So in the next section, we will see how to convert decimal into hexadecimal using floating point numbers. So here, we are given with the number 0.93 in decimal and we have to convert it into hexadecimal. So we will take the number 0.93 and we will multiply it with 16. Why with 16? Because base of hexadecimal is 16. So that's why we will multiply it with 16. So we get the number 14.88. Now the integer part is 14, or you can say E, and the fractional part is 0.88. So is the fractional part is equal to 0? No, the fractional part is not equal to 0. So we will multiply the fractional part again with 16 and we get the answer 14.08. Now the integer part is 14, or you can say E, and the fractional part is 0.08 here. So is the fractional part is equal to 0? No, the fractional part is not equal to 0. So again we will take the fractional part and we will multiply it with 16 and we get the answer 1.28. So now the integer part is 1, so we write 1 here, and the fractional part is 0.28. So we write 0.28 here. So again, is the fractional part is equal to 0? No, not 0. So we will take the fractional part and we will multiply it with 16 and we get the answer 4.48. So 4 is the integer part and 0.48 is the fractional part. Now, is the fractional part is equal to 0? No, the fractional part is not equal to 0. So again, multiply it with 16 and we get the answer 7.68. So 7 comes here and 0.68 comes here. So now we can see that the fractional part is not equal to 0. And we also see that the fractional part is not ending. So we will stop the procedure. If the fractional part is not equal to 0 till 5 calculations, as we can see that till 5 calculations the fractional part is still not equal to 0 and it is not ending. So we will calculate it till 5 numbers and then we will stop. So we will stop in 2 cases. The first case is that the fractional part is equal to 0 and the second case is that the fractional part is not ending. So we will multiply it 5 times and if still it is not equal to 0, then we will stop the procedure. So doing it 5 times is enough if it is not ending. But you can do it more if you want to do that. But that is enough as long as calculations are concerned. You don't need to go ahead. Alright? So again we will calculate the answer by going from top to bottom of the integer part. So the decimal point will maintain its place and we can write the answer as 0.EE147. As you can see here, 0.EE147 in hexadecimal. So now we can say that the number 0.93 in decimal is equal to 0.EE147 in hexadecimal. So this is how we can convert decimal into hexadecimal using floating point numbers. So now we have converted decimal into other bases using whole number as well as decimal into other bases using floating point numbers. But the floating point number we used were 0 point something. Okay, the number comes after the decimal point. But we did not cover the numbers that have whole numbers as well as floating point numbers. Just you can see this number. This number has the whole part 198 and the floating part 0.625. So we have not done the conversion of such numbers. We did them separate, right? So what if we are given with the number that has integer part, or you can say whole part, as well as fractional part? How will we solve it? So let's see how will we solve such numbers that have whole part as well as fractional part. And we have to convert the decimal number into other base. For example, in binary, in octal or hexadecimal. So we will solve it in the following way. We will take the integer part. For example, in case of this number, we will take 198 and we will solve it using which method? That is prime factorization method. Okay. Once done, then we will move ahead and we will solve the fractional part 0.625 using the conversion method of decimal into other bases for floating point numbers. So we will solve this part using prime factorization and this part using conversion of decimal into other bases for floating point numbers. So once we will calculate answer from here and we will calculate answer from this part, then we will combine both the answers to get the final result. So we will combine both answers to get final answer. Alright, I hope you understand. But if you have any confusion, then we will look at some examples and then you will understand it properly. So let's move ahead. So in this example, we are given with the number 198.625 in decimal and we have to convert it into binary. Remember, when we were converting decimal into binary, then we did this whole number separately and we did this floating point number separately. So in this example, we will see that if we are given a number that has a whole part as well as a fractional part, then how will we solve it? Alright. So remember, we did in the previous slides that we converted 198 in decimal into binary using this prime factorization method. And the result that we calculated was 11000110. So I will not tell you the procedure again because I have explained you in the previous slides. So we do not need to revise it. So we will calculate 198 using this method, that is the prime factorization method. And we will solve 0.625 using which method? That is this method that we did previously. Alright. We took this number and then we multiplied it with 2 by 2 because base of binary is 2, that's why. So again, I am not going into detail. How did we solve it? I already explained it to you. So the answer of this question was 0.101. So now we have the answer of 198, that is this one. And we have the answer of 0.625, that is this one. So while calculating the final answer, we will combine this answer and this answer together. And this is how we can solve a decimal number that has the whole part as well as a floating part. So I hope you understand. Okay. So let's look at our next example in which we are going to convert decimal into octal using a number that has a whole part as well as a fractional part. Alright. So we have the number 798 and we did it previously that we solved 798 using prime factorization method and we calculated the result 1436 in octal. And we solved the floating part using this method in which we converted 0.015625 into octal and the result was 0.01. Again, I will not explain the procedure because we have already done it and we do not need to do it again. So once we calculated the answer of 798, that is 1436, and calculated the answer of the floating point, that is 0.01. So we will calculate the final answer by combining both the answer, this answer and this answer. So the final answer is 1436 comes from this side and 0.01 comes from here. So the final answer is 1436.01 in octal. So this is how we can convert decimal into octal using numbers that have whole part as well as fractional part. So let's see how to convert decimal into hexadecimal using numbers that have whole part as well as fractional part. So we remember that we converted 798 in decimal into hexadecimal. So this number has the whole part 798 and in the previous slides I made you understand how we converted 798 in decimal into hexadecimal using prime factorization method and the result we got was 31e in hexadecimal. Alright, once we calculated the whole part, then we will look at the fractional part and we will solve it using this procedure that I already explained to you, so we do not need to repeat it. So the answer of 0.93 in decimal into hexadecimal is 0.147. So once this answer is calculated and this answer is calculated. So finally we combine this answer and this answer to get the final answer. So now in this final answer we can see that 31e comes from here and 0.147 comes from here. So we combine this answer and this answer to get this final answer. And now we can say that the number 798.93 in decimal is equal to 31e.147 in hexadecimal. So this is how we can solve a number that is mixed, that has a whole point as well as a floating point. So we solved the whole number using this procedure and floating point number using this procedure, and then we combine this answer and this answer to get this final answer. So I hope you understand it. So now we have seen how to convert decimal into other bases using whole numbers as well as floating point numbers as well as a number that has a whole part as well as a fractional part. So in the next section we will see how to convert other bases into decimal. So now we are going to look at the solutions of assignment number 2. So first of all, we have question number 1 and we will look at its solution. So question number 1, in the question number 1, we have to convert an octal number into hexadecimal. And the number is 27.3 in octal and we have to convert it into hexadecimal. Now we know that octal into hexadecimal conversion is not direct. So first of all, we will convert octal into binary on this slide. And in the next slide, we will convert binary into hexadecimal. So this is the part A, and in that we are going to convert the octal number into binary. So here we have the number 27.3. First of all, we will look at the letter 2 and we will look into the table. So 2 is equal to 0, 1, 0 in binary. So we write here 0, 1, 0. Next we have the letter 7, and here we can find 7, and 7 is equal to 1, 1, 1 in binary. So we write 1, 1, 1. Next we have the floating point number, and then we have the digit 3. So where is 3 in the table? Here is 3, and 3 is equal to 0, 1, 1 in binary. So we write 3 as 0, 1, 1. So now we have calculated, we will combine this value, and this value to make the final answer. So now we can say that the number 27.3 in octal is equal to 010.111.011 in binary. And in the next slide, we will convert it into hexadecimal. So this is the part B of the question, and in that we will convert this number into hexadecimal. So here we write the number in the form of groups. Each group contains 4 bits, and we will make the groups while moving away from the decimal point. Okay. So first of all, we make group of 1110. So here is 1110. So this group has 4 bits. Next, only 10 is left here. So we know that we need to make group of 4 bits. So we will add 2 zeros here to make it a 4-bit number. And next we see towards the right side of the decimal point that we have the number 011. Again, it has 3 digits. We need to make it 4. So we add 10 to it. So now we have made the groups. Next we will look at the table and find its equivalent hexadecimal value. So first of all, we look at 0001, which is where? Here in the table, and it is equal to 1. So we write 1 here. Next we have 0111. So in the table we can find 0111 here, which is equal to 7. So we write 7 here. And in the last one we have 0110. And if we look at 0110 in the table, here is 0110 in the table, and 0110 is equal to 6. So we write 6 here. Now there is some mistake of the errors. Please don't consider them. Just consider what I am writing with my pen. So now we have calculated the number, and now we can say that this binary number is equal to 17.6 in hexadecimal. And we can also say that the number 27.3 in octal is equal to 17.6 in hexadecimal, as we converted this octal number into binary first, and then this binary number into this hexadecimal number. Okay, next we move to the solution of question number 2. So here we have to convert a hexadecimal number into octal. And we know that when we are going to convert hexadecimal into octal, then first of all, we will convert hexadecimal into binary, and then this binary into octal. So here is the part A. First of all, we will convert hexadecimal into binary first. Okay. So we have the number 2F.9 here. So we will look at the table. Where is 2 in the table? Here is 2 in the table, and it is equal to 0010. So we write here 0010. Next we have the digit F, and we will go to the digit F in the table, and F is equal to 1111. So we write it here. Next we have the digit 9. So here is 9 in the table, and 9 is equal to 1001. So we write here 1001. Now we will combine this value, and this value to calculate our final answer. So now we can write here 00101111.1001. Okay. So now we can say that the number 2F.9 in hexadecimal is equal to this number in binary. While calculating the final answer, we have omitted these 2 zeros. They are extra. You can add them, and if you don't add them, still the value of the number will remain the same. Okay. Now in the next part B, we are going to convert this binary number into octal number. Okay, so we are going to make the groups of this binary number, and each group has 3 bits while moving away from the decimal point. So first of all, we will move towards the left side of the decimal point. First of all, we have 1 1 1, so we write here 1 1 1. Next we have 1 0 1, so we write here 1 0 1. And then we have, while moving towards the right side of the decimal point, we have the number 1 0 0, so we write here 1 0 0. And then we have the number 1, so we write here 1. So we need to make group of 3 bits, so we add 2 zeros to that. Alright, so now we have completed the groups, and we will look at the table and find out their octal equivalent. So first of all, we have 101. Where is 101 in the table? Here is 101, and it's equal to 5, so we write 5 here. Next we have 111, so here is 111 in the table, and it is equal to 7, so we write 7 here. Next we have 100, so here is 100, and it is equal to 4, so we write 4 here. And again we have 100, so here is 100, so we can write 4 again. Next we will combine this value to calculate our final answer, that is 57.44. So this binary number is equal to 57.44 in octal, or in other words we can say that the number 2f.9 in hexadecimal is equal to 57.44 in octal. So as we know that first of all we converted this hex number into binary, and then binary number into this octal number. Next we move to question number 3 solution, and here we have to convert our decimal number into binary. So we can see that we have to convert a decimal number 67, and we have to convert it into binary. So first of all, we will place it here, and we will divide 67 by 2. So we can see that the quotient is 33 and remainder is 1. Next, 33 is divided by 2, and then quotient is equal to 16 and remainder is equal to 1. Next, 16 is divided by 2, so quotient is equal to 8 and remainder is equal to 0. Next, again we divide, so quotient is equal to 4 and remainder equal to 0. Then again 4 divided by 2, quotient is equal to 2, remainder is equal to 0. When we divide 2 by 2, so we have the quotient is equal to 1 and remainder is equal to 0. So now we will calculate the value while moving like this from bottom till top. So we will calculate the answer like 1 0 0 0 0 1 1. So as you can see that the answer is 1 0 0 0 0 1 1 in binary. So this is how we can convert the decimal number 67 into this binary number. Next we have question number 4, and in this question we have to convert the decimal number into octal number, right? So we are given with the number 652 in decimal, and we have to convert it into an octal number. As we have to convert it into octal, so we will divide the number by 8. So quotient is equal to 81, remainder is equal to 4. Again 81 is divided by 8, so quotient is equal to 10, remainder is equal to 1. So again 10 is divided by 8, so quotient is equal to 1 and remainder is equal to 2. And again we will calculate the answer by moving like this from the bottom till the top. So the answer is 1 2 1 4 in octal. So now we can say that the number 652 in decimal is equal to 1214 in octal. So this is how we can solve question number 4. Next we move to question number 5, and here we have to convert a decimal number into hexadecimal. So the decimal number given is 55 and we have to convert it into hexadecimal. As we have to convert it into hexadecimal, so we will divide 55 by 16. So when we divide it, quotient is equal to 3 and remainder is equal to 7. As 3 is smaller than 16, so 3 cannot be divided by 16 again, and we will stop the process. And we will calculate the answer by moving from bottom till top like that. So here we can say that the answer is 37, or you can say 37. So the number 55 in decimal is equal to 37 in hexadecimal. So this is how we can convert it. So now we have seen how to convert decimal into other bases using whole numbers as well as floating point numbers, as well as a number that has a whole part as well as a fractional part. So in the next section, we will see how to convert other bases into decimal. So first of all, we will see how to convert binary into decimal, and then octal into decimal, and then hexadecimal into decimal. So let's move ahead. So first of all, we will look at how can we convert a binary number into a decimal number. So let's move ahead. So now we will see how to convert binary into decimal using whole numbers as well as floating point numbers. So first of all, we will see how to convert binary into decimal using a whole number. As you can see in the question, we are given with a binary number 1011 in binary, and we have to convert it into decimal. So first of all, we see how to solve the whole number into decimal. So we are given with the whole number 1011. We will start from the rightmost digit, that is 1 here, and multiply it to 2 raised to power 0. In this way, we will take digits from right to left and will multiply with powers of 2 starting from 0, then 1, then 2, and then so on. So using this technique, let's solve the question. So when we will solve the question, then you will understand the technique. So let's solve it. First of all, we will take the digit 1 and we will multiply it to 2 raised to power 0. Alright. And then we will take the next digit, that is 1, and then we will multiply it to 2 raised to power 1. So the first digit was multiplied with 2 raised to power 0, and the next with 2 raised to power 1, and the next, that is 0, we multiply it to 2 raised to power 2, and the last digit, that is 1, we will multiply it to 2 raised to power 3. And as you can see that the powers of 2 are increasing from right to left. They are starting from 0 and then moving ahead. So 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, and 2 raised to power 3. So in this way, we will solve all of the questions that have whole numbers. So once we multiplied them, then we will add them all together. So we know that 2 raised to power 0 into 1 is equal to 1, 2 raised to power 1 is equal to 2, and 2 into 1 is equal to 2. Next we have 2 raised to power 2 is equal to 4, and 4 into 0 is equal to 0. Next 2 raised to power 3 is equal to 8, and 8 into 1 is equal to 8. Now we add them all together. 8 plus 0 is equal to 8, and 8 plus 2 is equal to 10, and 10 plus 1 is equal to 11. So the final answer is 1, 1, and we can say that the number 1011 in binary is equal to 1, 1 in decimal. So now we have seen how to convert binary into decimal using whole number. In the next question, we will see how to convert a floating point number into decimal. So here we are given with the number 0.101. So while doing the fractional part, we will start from the leftmost digit, which is 1 here, and multiply it to 2 raised to power minus 1. In this way, we will take digits from left to right and will multiply with powers of 2 starting from minus 1, then minus 2, minus 3, and so on. So remember, in case of whole number, we have a floating point here, which is normally optional. We can write it or we can omit it. Alright. So we will multiply the numbers with powers of 2 while going away from the decimal point. right? That is from right to left side. And in case of fractional number, we will move away from the decimal point, that is from left to right side. Alright, so remember this point just like we did it previously. So in the same way, we will move away from the decimal point. So first of all, we will take the number 1 and we multiply it to 2 raised to power minus 1. And then we take the number 0 and we multiply it to 2 raised to power minus 2. And then we take the number 1 and we multiply it to 2 raised to power minus 3. The difference between this method and this method is that the negative powers are used here, and here we use the positive powers. So after multiplication, we will add all of them together. So we know that 2 raised to power minus 1 into 1 is equal to 1 by 2, or you can say 0.5. And next, 2 raised to power minus 2 into 0 is equal to 0. And next, 2 raised to power minus 3 into 1 is equal to 1 by 8. Alright, so we add them all together and we get the final answer as 0.625. So we solved the whole number using this procedure and we solved the fractional number using this procedure. Now let's move towards the question number 3, in which we have to convert a number 1011.101 in binary and we have to convert it into decimal. So we can see that this number has a whole part as well as a fractional part. So we will solve this whole part using this procedure and the fractional part using this procedure, in which we will use the negative powers of 2. So finally we will combine. So 1011 will be solved using this procedure and its answer is 11. And 0.101 is solved using this procedure and the answer is 0.625. So when we convert this number into decimal, then we will combine this answer and this answer to get the final answer. That is 11 comes here and 0.625 here. So these two answers are combined to get the final answer, and now we can say that the number 1011.101 in binary is equal to 11.625 in decimal. So this is how we can convert binary into decimal using whole numbers or fractional number or a number that has a whole part as well as a fractional part. So I hope you understand it. So now we have covered how to convert binary into decimal. In the next section, we will see how to convert octal into decimal. So now we have covered how to convert binary into decimal. In the next section, we will see how to convert octal into decimal. So now we will see how to convert octal number into decimal number using whole numbers as well as floating point numbers. So first of all, we are given with question number 1, in which we have to convert the number 106 in octal into decimal. So first of all, we will see how to solve the whole number. So we are given with the number 106. So in binary, we multiplied the numbers with powers of 2 because binary has the base 2. So here we are dealing with octal. So consequently, we will multiply the numbers not with the powers of 2, rather with powers of 8, because we are dealing with octal number, not binary. So in the same way, we will move away from the decimal point with increasing powers of 8 starting from 0. So first of all, we will multiply 6 with 8 raised to power 0. Next we have 0. So we will multiply 0 with 8 raised to power 1. And the next digit we have is 1. So we will multiply 1 with 8 raised to power 2. Alright, see, the powers of 8 are increasing starting from 0. So here it is 8 raised to power 0, 8 raised to power 1, 8 raised to power 2. So once done, we will add them all together. So 8 raised to power 0 is equal to 1 and 1 into 6 is equal to 6. Next we have 8 raised to power 1 is equal to 8 and 8 into 0 is equal to 0. Next we have 8 raised to power 2 is equal to 64 and 64 into 1 is equal to 64. So now we will add them. 64 plus 0 is equal to 64 plus 6, that makes 70. Alright, so the number 106 in octal is equal to 70 in decimal. So once we have seen how to convert octal into decimal using whole numbers, next we will see how to convert octal into decimal using floating point numbers. So here we are given with the floating point number 0.32 in octal and we have to convert it into decimal. So the number given is 0.32. Again, we will move away from the decimal point, that is from left to right in this case, and we will multiply the first number with 8 raised to power minus 1 and the second number with 8 raised to power minus 2 and so on. So first of all, we will take the number 3 and multiply it with 8 raised to power minus 1. So again you can see that here we are using the power of 8. Why? Because we are dealing with octal numbers and octal numbers have the base 8. That's why. So next we take the digit 2 and multiply it to 8 raised to power minus 2. Right? So no more digits are there, so we will stop the procedure and we will add them all together. So by solving this, we get the answer 3 by 8 and by solving this, we get the answer 2 divided by 64. So we will add them and the final answer we will get is 0.40625. So now we can say that the number 0.32 in octal is equal to 0.40625 in decimal. So now let's move to question number 3. Here we can see that we are given with a number that has a whole part as well as a floating point part. So the answer of the whole part 106 will be calculated using whole number part. So as we know that the answer of 106 is 70. Alright, and the number 0.32 is calculated using the fractional number part. So the answer of 0.32 in octal is equal to 0.40625. So we will combine both the answers and we can write that the number 106.32 in octal is equal to 70.40625 in decimal. So question number 3 is for the situation in which we have a number that has a whole part as well as fractional part. So remember, we will solve the whole part using this procedure and the fractional part using this procedure, and then we will combine both the answer just like 70 comes from here and this answer comes here. So this is how we can convert octal into decimal using whole numbers and floating point numbers. So in this section, we will see how to convert a hexadecimal number into decimal using whole numbers as well as floating point numbers. So let's move ahead. So now we will see how to convert a hexadecimal number into decimal using whole numbers as well as floating point numbers. So first of all, we will see how to convert a whole number into decimal number. So we are given with the whole number 13a. And once again, while moving away from the decimal point, we will multiply the digits with powers of 16 starting from 0 till onwards. Alright, so we will take the number a and multiply it with 16 raised to power 0. And remember, in hexadecimal, a is equal to 10. Next, we will take the digit 3 and multiply it with 16 raised to power 1. So again, the powers are increasing starting from 0 and increasing by 1 while moving towards left. So we will multiply 3 with 16 raised to power 1. Next we will take the digit 1 and multiply it with 16 raised to power 2. So can you tell me why are we using the number 16? Because We are using the number 16 because hexadecimal has the base 16 and we have to convert a hexadecimal number into decimal, so we are using the number 16. Alright, so once we did that, we will add them all together. So now we can see that 16 raised to power 0 is equal to 1 and 1 into 10 makes 10. Next we have 16 raised to power 1 is equal to 16 and 16 into 3 is equal to 48. Next we have 16 raised to power 2 is equal to 256 and 256 into 1 is equal to 256. And once we add them all together, we get the final answer 314. So now we can say that the number 13a in hexadecimal is equal to 314 in decimal. So now we will see how to solve the fractional part. In this question, we are given with the number .B8. As you can see here, .B8. And once again, while moving away from the decimal point, so in this case, we will move from left till right and we will multiply the numbers with negative power of 16, starting with 16 raised to power minus 1 and so on. So first of all, we will take the number b and multiply it with 16 raised to power minus 1. And as you know that b is equal to 11 in hexadecimal. So 11 is multiplied with 16 raised to power minus 1. Next we take the digit 8 and we multiply it with 16 raised to power minus 2. Right? As we are moving away from the decimal point, so initially the power was minus 1 and now it has become minus 2 here. So then we will add both the values. Alright. So here the value is 11 by 16 and here the value is 8 divided by 256. So after adding them all together, we get the final number 0.71875. So now we can say that the floating number .B8 in hexadecimal is equal to 0.71875 in decimal. So now let's look at question number 3, in which we are given with the number 13a.B8 in hexadecimal and we have to convert it into decimal. So what we will do, we will combine question number 1 and question number 2, right? So we will solve 13a using this procedure and we will solve .B8 using this procedure. So as we have already calculated the values, so we will combine this answer with this answer. So now we can say that the final answer is 314 comes here, 314, and 0.71875 comes here. So now they are combined to get one answer and we can say that the number 13a.B8 in hexadecimal is equal to 314.71875 in decimal. So this is how we can convert hexadecimal into decimal using whole number and a fractional number that does not have a whole part. And also we saw how to solve a number that has a whole part as well as a fractional part. And once again I repeat that we solved the whole part using this procedure and the fractional part using this procedure, and then we combine this answer and this answer to get the final answer. So now we look at the solutions of assignment number 3. And first of all, we look at the solution to question number 1. So in question number 1, we are given with a decimal number and we have to convert it into binary. The number given is 0.25 and we have to convert it into binary. As the number is floating point, so we will use this procedure. So first of all, we will multiply the number with 2. Because we are converting it into binary, so we will multiply it 2. 0.25 into 2 is equal to 0.5. So in this case, we can see that the integer part is 0 and the fractional part is 0.5. So is the fractional part is equal to 0? No, it is not 0. So now 0.5 will come here and we will multiply 0.5 with 2. So 0.5 into 2 is equal to 1.0. So integer part is equal to 1 and fractional part is equal to 0. Now, yes, the fractional part is equal to 0. So we will stop the process. And we will calculate the answer by going from top to bottom of the integer part. So we can write the answer as the decimal point will maintain its position. So point will stay here, and we can write the answer as point, and first we write 0. 0 comes here, and then we write 1. So 1 comes here. So now we can say that the number 0.25 in decimal is equal to 0.01 in binary. Next we move to question number 2 solution. So in this question we have to convert our decimal number into octal. So this is the decimal number 0.16. So as the number is 0.16 and we have to convert it into octal, so we will multiply the number by 8. So first of all, we have the number 0.16 and we will multiply it by 8 and we get the answer 1.28. So now the integer part is 1 and fractional part is 0.28. So is the fractional part is equal to 0? No. 0.28 comes here and again we multiply it with 8 and we get the answer 2.24. So the integer part is 2 and fractional part is 0.24. Again not 0, so 0.24 will come here and we will multiply again with 8 and we get the answer 1.92. So integer part is 1 and fractional part is 0.92. Again not 0, so 0.92 will come here and we will multiply it with 8. So it is equal to 7.36. So integer part is equal to 7 and fractional part is equal to 0.36. Again not 0, so we will multiply 0.36 into 8 and the answer is 2.88. So integer part is equal to 2 and fractional part is equal to 0.88. So now we can see that the process is not ending and fractional part is once again not 0. So we will stop the procedure when we will do the steps 5 times, okay? Otherwise it's a never ending procedure and it will keep on going on. So we will stop it and we will calculate the answer by going from top till bottom in this direction, okay? So now we can say that the answer is decimal point will maintain its position 0.12172 in octal. So this is how we can solve question number 2. Next we move to question number 3 solution. And we can see that we are having a binary number and we have to convert it into decimal. The binary number is 1001.011. Now we will solve this whole number part using this procedure and this fractional number part using this procedure, okay? So first of all, we look at the whole number 1001, okay? So what we will do here is that we have to convert this binary into decimal. So we will multiply it with powers of 2 starting from 0 and increasing by 1 while moving away from the decimal point. So first of all, we have 1 here. So we will multiply it 2 raised to power 0. Then we have 0 here. So we will multiply it to 2 raised to power 1. And see the powers are increasing. And then we have 0 here, so we will multiply it 2 raised to power 2. And then we have 1 here, so we will multiply it 2 raised to power 3. Okay. So, and then we will add them all together with each other. So now this becomes 8 and then 0, 0 and then 1. And when we will add it, it becomes 9. Okay. So the answer of the whole number is calculated. Now next we will calculate the answer of this fractional number, that is 0.011. So we write it here and we know that we multiply it to negative powers of 2 while moving away from the decimal point. So first of all, we multiply 0 with 2 raised to power minus 1, and then 1 with 2 raised to power minus 2, and then 1 with 2 raised to power minus 3, and then we add them together. Okay, so this is equal to 0, and this is equal to 1 by 4, and this is equal to 1 divided by 8. So if we calculate the answer by adding these three values, it becomes 0.375. Now we will combine the answer of whole part and also the fractional part to calculate the final answer. So now we can see that 9 comes from here. So the answer is 9.375 comes from here. So this is how we can calculate the final answer, and we can say that the binary number 1001.011 in binary is equal to 9.375 in decimal. So now we move to the solution of question number 4. And in question number 4, we have to convert an octal number into decimal. The octal number is 751.52 in octal, and we have to convert it into decimal. So we will solve the whole number part using this procedure, and we will solve the fractional part using this procedure. Alright. So first of all, we solve the whole number part. So we have the number 751 here, and we will multiply each digit with powers of 8, starting while moving away from the decimal point. So first of all, we will multiply with 8 raised to power 0, then 8 raised to power 1, and 8 raised to power 2. So the first digit is 1, so we multiply 8 to 8 raised to power 0. And then the second digit is 5, so we multiply 5 with 8 raised to power 1. So the powers are increasing by 1 while moving away from the decimal point. So next we have the digit 7, so we multiply 7 with 8 raised to power 2. Okay. And then we will add them together to calculate the final answer. So here we have 448, and then here we have 40, and here we have 1. So after adding this and this and this, we get the final answer as 489. So this is the answer of the whole part. Okay. Next we have the fractional number 0.52. So here is the number 0.52 here, and we will multiply it with negative powers of 8 while moving away from the decimal point. So the first number is 5 while moving away. So we will multiply 5 with negative power of 8. So 8 raised to power minus 1. Next we will take the second digit 2, and we will multiply it to 8 raised to power negative 2. Okay. So here we get the fraction 5 by 8, and here we get the fraction 2 by 64. So we add them together and we get the final answer 0.65625. So now we got the answer of whole part and the fractional part. So we will combine them together to get the final answer by combining part 1 and part 2. So the final answer is 489 comes here, and then we have the decimal point, and then 65625 that comes here. So we combine the answer of part 1 and also part 2 to get this final answer, and we can say that the number 751.52 in octal is equal to 489.65625 in decimal. Next we move to the solution of question number 5. So in question number 5, we have to convert a hexadecimal number into decimal. The number is 1a.be, and again we will solve this part using whole number procedure and this fractional part using this fractional number procedure. Okay. So first of all, we have the number 1a, and as we have to convert a hexadecimal number, so we will multiply the numbers with increasing powers of 16 while moving away from the decimal point. So a is multiplied with 16 raised to power 0, and 1 is multiplied with 16 raised to power 1. and we add them together, and then we have 16 plus 10, and here we have the final answer 26. And here is the fractional number, that is point BE. So we will multiply these numbers while moving away from the decimal point with negative powers of 16. So first of all, we multiply B with 16 raised to power minus 1, and then we multiply E with 16 raised to power minus 2. Okay, and then we add them together, and here we get the fraction 11 by 16, and here we get 14 by 256, and then we add them, and then we get this value 0.7421875. Now again we will combine the answer of part 1 and also the answer of part 2, and we will get the final answer as 26.74211875 in decimal, which is the final answer. So again we have completed the solution, and thank you so much for your time. I hope you understand all of the solutions, and I hope you have done the assignment yourself. Thank you. So congratulations, we completed all of the conversions from one base to another, and here our course is almost complete. So let's summarize what we did in this course. First of all, we converted octal into binary and then binary into octal using table. In the next section, we converted hexadecimal into binary and binary into hexadecimal using table. In the next section, we converted octal into hexadecimal, but the conversion was not direct. So first of all, we converted octal into binary and then binary into hexadecimal. And then we converted hexadecimal into octal. Again, the conversion was not direct, so we converted hexadecimal into binary and then binary into octal to get the final result. Next, we saw how to convert decimal into other bases. So first of all, we converted decimal into binary, decimal into octal, and decimal into hexadecimal. And remember, the procedure used for conversion of decimal into other bases is different for whole numbers from the procedure of floating point numbers. We solved the whole numbers using prime factorization method and the floating point numbers using the other method. Then in the next section, we converted other bases into decimal. So we learned how to convert binary into decimal and then octal into decimal and then hexadecimal into decimal. So in this way, we covered all of the necessary conversions that were required to learn to conquer the concept of number systems. So thank you so much for your time. If you have any suggestion, then please let me know personally. But if you enjoyed the course, then do not forget to leave a review. Thanks again.